All right, let's work through this problem as an introduction to chapter 25 or a review of it or whatever. So let's look the problem over. The first thing we want to do in this case is we want to identify that we truly have matched pairs. Now, matched pairs can come in a variety of forms. We can have members of a population that are matched, like identical twins, husbands and wives, right and left hand, or right and left foot, or eyeball, left and left eyes of the same person. In this case, though, we have a bunch of subjects, all from the same population, men, and we'll say, let's refine it a little bit more, men who need exercise. And so we have measurements taken from them before and after. Now, this is another indicator that we have matched pairs. There's only one population involved here. There's not two. If we were going to do a two-sample t-test, we would have two populations, and we'd try to find if there's any difference between them. But in this case, we have one population of men, and we're measuring them before and after a treatment. So this is a controlled experiment. So the first thing to do is we have to do the preconditions on this. We have to satisfy one precondition, namely that we do have matched pairs. So we have a measurement before and after these every one of these individuals here. Now, these are volunteers for the program. They're not randomly selected, but we can safely say that they are independent of each other, and that the measurements, the before and after measurements, are not independent of each other. So we do have matched pairs. So we can also answer the question, is the sample of the differences between these before and after measurements is obviously not greater than 10% of all such differences that could exist in the population, since this is only a few people. So we've talked about independence. It's okay that they're volunteers for the program. The data that's generated is they're given the treatment before and after, and so on. So let's generate the differences, because the rest of the inference, namely the most important part, which is nearly normal, we have to do not on the before data and not on the after data. We must do it on the differences between the before and after. So let's put the before data in L1 as it is here, and the after data in L2. And then in L3, we're going to arrow over L3. And we're hoping that the pulse rates went down, that the exercise, that's one of the supposed effects of exercise, regular exercise, is that it makes your heart beat more efficiently, so your pulse rate goes down. So if we subtract L2 from L1, then we should expect a positive difference. So we're going to arrow up to the top here, so the L3 is lit up, and then we're going to put in L1 minus L2, and we're going to hit enter. And so now we have a list of differences between L1 and L2. In this list, L3 is what we're going to do inference on. So let's get out of here. So we're going to exit out of here, and let's do a histogram. Let's see what the histogram looks like on L3. And so I'm going to arrow over the histogram, and then now I have to go down to, I didn't hit enter on histogram, so let me go back and do that, hit enter. Now the X list that I want is L3, because that's where the differences are. So I'll hit enter there. Now we got to be prepared for this histogram maybe not looking so great. So let's see what it looks like here. Zoom. I got to do a zoom 9. And I bet I forgot to turn it on. I did. Okay. Zoom 9. Well, that doesn't look so good. It doesn't look terrible. It's not skewed. With only 11 measurements, it'd be hard to look. It would be hard for it to look normal. Let's see what the box plot looks like. Now, one thing I can do with this histogram, since the differences are so small, let me try this. Let me go to the window. And, okay, so the window is -1. Let's make this 11. And let's make the scale 1. And now let's see what this looks like. So the smallest measurement is -1, it looks like. Then we have this gap here. It looks sort of okay, actually, except we have this gap. So let's see what the gap's all about. So let's look at the box plot. Now remember, you want to choose the box plot that has little dots on it right there, because that'll show you outliers. And we're going to continue to do it on L3, so we'll do a zoom 9. Okay, there's no outliers. Okay, so the data looks, not terribly unsymmetrical. So now let's look at a normal probability plot and see how that looks. So I'm going to arrow down and then over to the normal probability plot and hit enter. And I like to use the y-axis. Okay, now you can see that there's a sort of a similarity here between this and the box plot, but this isn't bad. Let me take a picture of this. I'd want you to draw a little picture of it yourselves. And then let's go back and let's take a picture of that histogram. Or let's take a picture of the box plot. Let's do that. So we have a normal probability plot. And then let's use the box plot to show us that we do not have outliers. So let me do a zoom 9 here. And I'll take a picture of this. And so that we can refer back to that later. All right. So on the basis of these two pictures, we can say that the data is nearly normal. So we have satisfied our preconditions. So we can say that the differences, which is, let me do a review. Now the list of differences, the average of the list of differences. Let's take a look at that. It's called H-bar. Of L3. Now let's run some single variable stats and one variable stats, and we're going to run it on L3. Let's take a picture of this. And what else is it showing us? I might as well take a picture of that too. And so here's what we have so far. So this X bar here that's listed in our output, that is really D bar. And S sub X is the standard deviation of the sample. So let's call that. So we'll say D bar, H bar is H bar. And we can get it off of here. 2.8. And S of H bar equals 2.53. And N equals 10. So the standard error of H bar is going to equal 2.53 divided by the square root of 10. obviously the degrees of freedom is going to equal 10 minus 1, which is 9. So the t-score, t sub 9, is going to equal, let's write our hypotheses first before we forget. Okay, so the null hypothesis, h sub 0, is that the difference, called d, is delta sub 0. Okay, so what are we saying? The average of the before and after differences of the men in the exercise program is 0. So what's another way to say this? Exercise does not lower the heart rate. The alternative hypothesis would be that delta is greater than 0. The average of the before and after differences of the men in the exercise program is greater than 0. In other words, exercise helps lower heart rate. Okay, so now we can say we're going to go for a t statistic. T sub 9 is going to equal d bar, which is 2.8 minus the null, which is simply 0, divided by 2.53 divided by the square root of 10, not n, 10, which is approximately equal to 2.8 divided by, open parenthesis, 2.53 divided by the square root of 10. Okay, so it's about 3.5. All right, now the p-value is going to equal TCDF. So we'll do second vars. TCDF number 6, 3.5, 99, 9 degrees of freedom. Enter. So it's about 0.003. Let's say alpha equals 0.05, the default alpha. With a p-value of 0.003, we reject the null. There is evidence that exercise helps lower the heart rate. All right. And that's it. Oh, let's do it with a, let's do it using the calculator. So we'll go stat and then tests. Now we're simply going to do a t-test, number 2, and we'll use data, and we're going to use L3 as our data. And the alternative hypothesis is that it's greater than 0. So let's calculate. Same t-score, same p-value, same statistics, everything's good. Okay? All right, so that's how to do the test. Let's do a confidence interval. Setting it up is fairly straightforward. Let's just do it on the calculator real quick. And we're going to do a t interval right there. Because it's one sample, we're going to use the data. Notice it's already set to L3. Let's go with the confidence level of 0.95 and let's hit calculate. So here's the standard deviation and the mean. D bar is X bar and so on. And so the confidence interval is from 0.99, call it 1, from 1 to 4.6. So we would say we are 95% confident that the true average of the differences between the before and after measurements of the men in the experiment is between 1 and 4.6. So in other words, on average, the average difference for each man in his before and after heart rate was between 1 and 4.6 points higher before than it was after. So anyway, the true difference is somewhere between those two numbers. And the meaning of the 95% level of confidence is that 95% of all similar samples of before and after samples will yield a confidence interval that contains the true average of the differences between the before and after measurements of the men in the exercise test.